And now we turn and look at the simple classification of substances. We indicated that matter mostly exists combined in mixtures. The pure things we see were once combined into mixtures. They were then subjected to processes that aim at obtaining each component of the mixture as a separate entity. Substances are often classified into groups and families based on their shared properties, be it physical or chemical. Mixtures. We said that mixtures are substances existing together but not chemically combined. Notice we also said that matter can exist either as solid, liquid, or gas. These mixtures can either be solid-solid, solid-liquid, solid gas, liquid-liquid, liquid gas, or gas-gas mixture. Notice also that when a solid like salt dissolves in water, the product is a mixture. Nothing new has been formed and they can be separated by physical means. Separation of solid-solid mixtures. Common methods for separation of solid-solid mixtures include sieving, winnowing, and picking. The method adopted depends on the size of the particles in the mixture. Generally, the physical properties of the components of a mixture determine the method to be used in separating them. Separating iron fillings and sulfur. A mixture of sulfur and iron fillings can be separated by use of a magnet which will attract the iron fillings, leaving behind the sulfur powder. So there you have the dark iron fillings and the yellow powder of sulfur. We want to mix them. We want to make a mixture of iron fillings and sulfur. There you put the sulfur and add the iron fillings. And then you mix them properly. We mix them properly to make a mixture of iron fillings and sulfur. There we have it. We are going to use a magnet to attract the iron fillings and leave the sulfur powder behind. So there you have the magnetic iron fillings picked by a magnet and sulfur is left behind. The sulfur powder does not have a clean yellow color. Why? Because of the impurities of ions. So that's a method of separating iron fillings from sulfur by use of a magnet which attracts the iron fillings and the sulfur powder is left behind. Next is the separation of sodium chloride and iodine. When solid iodine is heated, the shiny black crystals vaporize into a purple gas. On cooling, the purple vapor reforms into the shiny black crystals. Iodine does not form liquid and this phenomenon is called sublimation. A mixture of sodium chloride and iodine crystals can then be separated by heating. The iodine will vaporize and condense on the cooler parts of the leaving behind the salt. That's perfect. Other substances that undergo sublimation are anhydrous iron 3 chloride, aluminum chloride, benzoic acid, and carbon 4 oxide, otherwise known as dry ice. In particular, dry ice is used by ice cream vendors, preferably to ordinary ice. Why? Because it sublimes, leaving no wetness, which would otherwise dampen the ice cream. So next time you buy an ice cream from a vendor, be more observant. The next method of separation is the separation of solid-liquid mixtures. Now, when a solid is mixed with a liquid, it will either dissolve or not. A solid is said to be soluble if it dissolves in a liquid. It is insoluble if it doesn't. When it dissolves, a solution is formed. The solid is called a solute and the liquid is called a solvent. A solute plus a solvent makes a solution. Common solvents include water, ethanol, and propanol. Common solutes include sodium chloride, potassium nitrate, oxalic acid crystals, and naphthalene, amongst many others. The first method of separating solid-liquid mixtures is decantation. Decantation is a method used to separate a solid-liquid mixture where the solid is insoluble, for example, a mixture of sand and water. When allowed to stand for some time, the sand will settle at the bottom of the container and the water can be poured out carefully. It is, however, not a very efficient method. Let's take a look at this demonstration from the following animation. So there we have sand added to water. Sand will not dissolve in water. It is insoluble in water, and given time the sand will settle at the bottom of the beaker in a process called sedimentation. And now you can carefully pour out the water. And that is the process of decantation. We've indicated it's, however, not a very efficient method of separating the solid-liquid mixtures. Another method of separating an insoluble solid-liquid mixture is by use of filtration. It's a more effective method compared to decantation. How does it work? The mixture is passed through a filter paper. Why? Because only water will pass through and the sand will be left behind. So there you have the filter paper. You fold it to make a cone-like shape. Then you put it on a funnel, a filter funnel, and pour the mixture of sand and water, and you will see that only water will pass through and the salt will be left behind. One of the greatest challenge with this method is that it is very slow. This is a very slow method of separating insoluble solid from a liquid, for example water and sand. Another method we look at is evaporation. And evaporation is a method used to separate components of a solution. That is when a solid dissolves in a liquid, it can be separated by evaporation. For instance, when a solution of sodium chloride is heated, the water evaporates, leaving behind the solid salt crystals. So we have a solution of sodium chloride that we want to separate. The salt is dissolved in water and we are going to heat on that Bunsen flame, and we are going to heat on that ethanol burner. We expect the water to vaporize, evaporate into a gas, and the salt will be left behind. So the boiling tube, you need to hold it, pointing the mouth away from your own face, otherwise you can cause a serious injury of burns if the hot liquid splashes on your face or on that of your friend. And also notice the inclination of the boiling tube. It is not heated while standing vertically. It is inclined at an angle. The problem with this operation is that it is quite expensive and also slow. You need a lot of heat energy to evaporate a lot of water. But this method can be used to obtain salt from seawater, which is very salty. We will still heat our liquid, our solution, until all the liquid has evaporated. You realize we only have little volume of the solution, and yet it takes quite some time. So the water has started evaporating. It's boiling, you could see. And we will expect the salt to be left behind. We're able to see the white crystals of sodium chloride on the walls of that boiling tube. Now the boiling is imminent. So there you have the salt. We cool the boiling tube in cold water, and let me see if we can get a better shot of that. We have the salt. The water has evaporated and has left behind the salt. Now the next separation procedure incorporates two methods of separation, that is filtration and evaporation. Now we look at separation of sand and sodium chloride. Now suppose you have this mixture and wish to separate them. You cannot use a magnet because neither is magnetic. You cannot heat directly because neither will sublime. However, we know that sodium chloride is soluble in water but sand is not. Therefore, we can add water to the mixture to dissolve sodium chloride. We then filter out the sand particles through filtration. The filtrate will be sodium chloride solution, and if we evaporate the solution, we will be left with the salt. So there you have a mixture of sand and salt. So we add water to dissolve the salt, a certain volume of water, and then you shake that to dissolve the sodium chloride, that is the table salt. Looks like you're gonna need more water. Add more water. Now that looks fine. So the first procedure is filtration. Take a filter paper and fold into a cone shape. Yeah, that's right. Fold the other side as well. So now you place that in a filter funnel. Place that in a funnel, and then you pour the mixture. Now just filter a little bit of it because we want to save on time. The process is quite fast in the beginning but gets slow along the way. Yeah, just take a small volume. That's right, that should be okay. Yeah, that should be okay. Now you then heat that, put the ethanol burner below that stand, that tripod stand, and the wire used to ensure even distribution of it. So we hit the now the salt crystals have already started forming as the water is evaporating. Just give it time. There you can see the crystals on the walls of that bowl. We need to evaporate all the water. So burner now. You can use your hands to remove it. Now let's see if we can get a better shot of the salt that has remained behind when the water evaporated. Yes, there you have it. The camera can get a better shot of that. So we have one of the components of the mixture, that is the salt, sodium chloride. And let's see the filter. Does it have any sand? There you can see in the filter paper we have the sand that filtered out. And there is also some at the bottom which decanted. So that's a method of separating, or rather a procedure of separating sand and salt that incorporated two methods. The first one was filtration. We filtered out sand and we got the filtrate being a solution of sodium chloride. Sodium chloride dissolved in water, and then we incorporated the second method of separation, that is evaporation. So we obtained the components of that mixture separately. Now the other method we need to mention is crystallization, and this method is used to separate most soluble substances from their solutions. When a mixture of copper 2 sulfate is heated, the water evaporates. If a glass rod is dipped frequently, at one point crystals will form on it. At this point, the solution is said to be saturated. A saturated solution is one that cannot dissolve more solid at a given temperature. Very, very important keyword there, temperature. Crystallization method is applied in obtaining sugar from sugarcane, extraction of salt from salty water, and extraction of medicinal substances from plants. The next method is obtaining solvents from solutions. And now in all the experiments we have conducted above, we have been obtaining the solid part of the mixture. So how can we get the solvent part of the solution? The first method we look at is distillation, and distillation is a method used to separate a solid from a solvent. When a solution of sodium chloride is heated, the steam formed can be cooled and collected while the sodium chloride salt is left behind. To make the cooling effective, a Liebig condenser is used. The liquid obtained is called a distillate. So there is the apparatus setup for a distillation experiment. The solution is contained in the round bottomed flask. The round flask is again connected with the Liebig condenser, linking it to the beaker on the other end. Notice also the flow of water in the opposite direction to the steam. The steam will flow through the Liebig condenser and cooling will occur. The steam will condense into a liquid and will be collected on the other end. So we will see droplets of the liquid, that is the solvent part of the flowing into the beaker. The next type of a mixture is a liquid-liquid mixtures. There are two types of liquid-liquid mixtures. Miscible liquids mix forming a uniform or homogeneous mixture, for example water and milk, water and ethanol. Immiscible liquids do not mix and usually form distinct layers. The denser liquid occupies the bottom layer, for example water and kerosene, water and paraffin, vegetable oil and water. Separation of immiscible liquids. When a mixture of water and oil is transferred into a separating funnel and allowed to stand for a while, two distinct layers are formed. The bottom layer is water and the upper layer is oil. A separating funnel can be used to separate the two layers by draining the lower layer, leaving the upper one. The separating funnel is used to separate the components of a mixture between two immiscible liquid phases. One phase is the aqueous phase while the other is an organic phase. The separation is based on the difference in densities of the two liquids. The liquid with the less density occupies the upper layer. The liquid with more density occupies the bottom layer. In this procedure, we are going to need a beaker, a filter funnel, a separating funnel, mixture of water and oil, and then we shall need a stand with a clamp. So clamp the separating funnel on the stand and then put a filter funnel on the mouth of the separating funnel and then add the mixture of water and oil. Put the mixture of water and oil in the separating funnel. Close the separating funnel with a cork. And now remove the separating funnel from the stand. Invert it and shake the mixture gently. Now open the tap to release the air and return the filter funnel with the mixture on the clamp. Allow the mixture to stand for some time and you realize it separates into two components, the upper layer and the lower layer. The upper layer is the oil and the lower layer is water. Now take a beaker and place it under the tap and open the tap to drain the bottom layer, that is water. Now close the tap when you're getting closer to the interface. Now take another beaker and collect the component of that is oil. Finally, label the two of the mixture, that is water and oil. Now, decantation can also be used to separate such components of a mixture by carefully pouring out the top layer. Again, it's not a very efficient method. Now we look at separation of miscible liquids and we look at fractional distillation. Water and ethanol are miscible liquids. To separate such a mixture, we take advantage of one important difference in physical property: boiling point. Water boils at 100 degrees Celsius at sea level, while ethanol boils at 78.2 degrees Celsius. The mixture can thus be distilled in fractions where ethanol vaporizes out fast and the water follows. This method is called fractional distillation. Fractional distillation is a method used to separate the components of a miscible liquid mixture whereby the difference in boiling points is less than 25 Kelvin. The apparatus for fractional distillation is similar to that of simple distillation, only that a fractionating column is put in between the round-bottomed flask and the distilling head. So we shall need a mixture of water and ethanol, 2 round-bottomed flasks, a stand with a clamp, a fractionating column, a distilling head, porcelain chips, a thermometer adapter, a Liebig condenser, a vacuum adapter, and a heating mantle. So we take the mixture of water and ethanol and pour into a round-bottomed flask. Put some porcelain chips, and then connect the fractionating column. Now put the distilling head and a thermometer adapter. Connect with the Liebig condenser and ensure the water will flow in a countercurrent. Completed the setup with the beaker at the end. Select the first fraction of the mixture and then connect the tubes, the rubber tubes, to the Liebig condenser for cooling, and open the tap to ensure water is flowing through the condenser. Now heat the mixture. Once it starts boiling, ethanol will distill out fast at 78.2 degrees Celsius. Any water trying to vaporize before 100 degrees Celsius will be cooled down in the distillation or the fractionating column and will flow back. So the first fraction, that is ethanol, will be collected first, and therefore you can see we are able to separate the mixture between water and ethanol. It may be necessary to repeat the separation twice to ensure efficiency. The fractionating column allows water, any water that vaporizes before 100 degrees Celsius is attained, to condense and flow back into the round-bottomed flask. It is packed with glass beads to increase the surface area for condensation. The Liebig condenser uses countercurrent flow for effective cooling. This method is applied in distillation of crude oil to obtain the fractions such as petrol, diesel, and cooking gas. It is also used in recycling used oil and separation of liquid air to obtain nitrogen and oxygen. Solvent extraction. Nuts contain oils. These oils can be obtained from the nuts by a method called solvent extraction. Oil is insoluble in water, but it is soluble in organic solvents such as propanol. If the nuts are crushed and propanol added, the oil dissolves. The solution formed is left in the sun for the solvent to evaporate, and the oil is left behind. Solvent extraction is applied in extraction of oils from nuts, extraction of natural dyes from plants, extraction of some herbal medicines from plants, extraction of caffeine from tea and coffee, and in dry cleaning to remove dirt. separation of colored substances, we look at chromatography. Now pay more attention. This is a very common section where questions hardly ever misses in chemistry examinations. Chroma means color and chromatography is the study of colors. A colored substance may contain a mixture of various substances. For instance, the green pigment in leaf extracts contain chlorophyll, the green pigment, and xanthophyll, a yellow pigment. The separation of these substances is achieved by chromatography. You must have done a part of this chromatography using a filter paper at primary school level. In chromatography, we exploit two properties of substances to be separated. One is the solubility of the substances in the solvent chosen. Each substance has varying solubility in any solvent. Next is adsorption of the substances on the adsorbent material used, like the filter paper. If a substance is highly soluble, it will travel further from the start point than the one that is less soluble. On the other hand, if a substance is strongly adsorbed on the adsorbent material, it will travel a shorter distance. Key terms include: the solvent front is the farthest point where the solvent reaches. A baseline is the point where the mixture is placed. The adsorbent material is dipped into the solvent, but the solvent must not touch the spots. The solvent rises up the adsorbent material and dissolves the mixtures. Each substance in the mixture is carried to a different height depending on its solubility and adsorption. If only one point appears, then the substance was not a mixture. It is a pure substance. The more the number of spots formed, the more the number of substances in the mixture. It is always necessary to run a known substance to aid in the identification of the components of the mixture. For instance, on your screen we have a setup for chromatography. M and T are the mixtures under study, and then we suspect that A, B, C, and D could be in M and T. There you have that, and we also have the solvent base. Now, when we dip this adsorbent material in the mixture, the solvent will have risen up to where the solvent base is indicated, and then given time, the solvent will rise through the adsorbent material. It reaches where the spots have been placed, dissolves them, and then continues to rise. It rises, and there we have our first spots. The solvent rises again, it goes, and there we have the second spots. It rises, continues to rise, and we have the third pair of spots. The solvent is still rising, it rises, and finally we have the fourth pair of spots. It will continue to rise. Any more spots? No. So the solvent reaches the maximum height, and that is the solvent front. Now we have the separation that has taken place. You can see the spots on the adsorbent material. Now, from this chromatography procedure, we can make the following inferences: that M is a mixture of B, C, and D. M is a mixture of B, C, and D. Why? Because you can see those spots. And then we say T contains only substance A. T contains only substance A, and therefore T is a pure substance. We can also conclude that D has the highest solubility and A had the lowest solubility. Why? Because A traveled the shortest distance, while D traveled the farthest. We can also say that A had strongest adsorption while D had the lowest. Now the above chart is very common in exams. Now check out as many questions as possible to ensure you understand it better.
The importance and role of communications through broadcasting. I learned that.
Understanding the balance between vision and expression. I learned that.
Exploring the issues of our time. I learned that.
How to think like a great designer. I learned that.
Integrating creativity with professionalism. I learned that.
That's what I learned.
From this chromatography experiment, we can say that M is a mixture of B, C, and D. Why? You realize that the column for M separated into 3 components. We have 3 spots. The first spot corresponds with the distance moved by B. Therefore, M contained B. Another spot along M corresponds to a spot. Another spot on M corresponds to one by C. They travel the same distance, which suggests that a component in M corresponds to that in C, and actually a component in M is actually C. The third spot in M corresponds to the distance traveled by the spot of D, and therefore M is a mixture of B, C, and D. T contains only substance A. T separated, or rather had one spot which corresponded to A, and therefore T is a pure substance. It was not a mixture.